Chapter 13 Solutions. Exercise 13.93. Use the Van 't Hoff factors in this table to calculate each colligative property. These are the Van 't Hoff factors of those chemicals in an aqueous solution. A non-electrolyte molecule does not decompose in water, therefore its Van 't Hoff factor is 1. Sodium chloride decomposes into two particles, a sodium plus cation and a chloride anion. Therefore, its theoretical value of the Van 't Hoff factor is 2. However, because this sodium chloride aqueous solution is not an ideal solution, so this Van 't Hoff factor deviates from 2. Over here we have magnesium 2 plus and sulfate 2 minus. With more charges on these ions, this value deviates from 2 more significantly. Over here, magnesium chloride decomposes in water and forms 3 particles. This is close to 3, so is this one close to 3. Iron chloride decomposes and forms 4 particles, 1 iron 3 iron and 3 chloride ions. So theoretical value should be 4, but it's 3.4 here. These values are determined using experimental data. Now the melting point of a 0.1 mole iron 3 chloride solution, what's the freezing point or melting point? So it's going to be 0 minus to emphasize the depression of the melting point. And we have 0.1 mole. This is mole. Theoretical value of Van 't Hoff factor is 4, but we have the experimental value 3.4. And then multiplied by the freezing point depression constant of water. It's 1.86 degrees Celsius per mole. You can find this constant in your textbook. The final answer should be negative 0.632. The osmotic pressure of a 0.079 mole potassium sulfate solution at 298 K. Pi denotes the osmotic pressure. The equation is pi equals CRT. Now let's plug in the concentration, the gas constant, and the temperature. C is 0.079 multiplied by the Van 't Hoff factor of potassium sulfate. Let's look it up. Potassium sulfate 2.6. R is 0.08206 atm liter over mole Kelvin. T must be in Kelvin. 298. The result is 5.0 atm. You can see this I in the equation as the Van 't Hoff factor. The boiling point of a 1.31% biomass magnesium chloride solution. The boiling point elevation is equal to the boiling point elevation factor, which is 0.512 degrees Celsius per mole, multiplied by the concentration of this solution in mole. We don't have that, but we have this mass percentage. We can assume 100 grams of solution and then 1.31 grams of magnesium chloride. We can convert it to the number of moles and then divide it by the mass of the solvent in kilograms. So here we assume 100 grams of water, 100 grams of solution multiplied by the percentage in mass. This is 0.0131. Now we have the mass of magnesium chloride. Now divided by its molar mass. Magnesium is 24.305. Chlorine is 35.45, and we have 2 of those. Now we have the number of moles of the solute multiplied by I, the Van Hoff factor, somewhere here, 2.7. Okay, and then divided by the mass of the solution in kilograms. We have 100 grams of solution minus this much solute. Alright, this is the mass of the solvent divided by 1,000 just to convert it to kilograms. Okay, now this whole thing is going to be the so-called effective molality of this solution. I call it effective because over here we have this Van Hoff factor being included. Now this multiplied by 0.512. We'll get the boiling point elevation. It's only 0.19 degrees Celsius. It's not much. Only because this is a fairly diluted solution, and also the boiling point elevation factor is pretty small. Alright, over here you get the molality of this magnesium chloride multiplied by the Van Hoff factor and then multiplied by the boiling point elevation constant. And you have the boiling point elevation of 0.19 degrees Celsius. The baseline is 100.